Okay, let's see what we cover in our last lecture. Okay, so in the last lecture, we talk about the data compression, right? So we give you the proof of the data compression. Okay, yeah, so this is in our chapter 5. Okay, so just at the very beginning part of chapter 5. So I think, I don't think in the book they discuss our proof approach, right? So they use a different proof approach by constructing, other kinds of code, but we're going to go over that later in our class. So, and then we start talking about the sources with memory, right? So that is in chapter 4, okay? So I think pretty much within, probably, so now 16, yeah. So we'll spend a few more lectures to finish chapter 4 and chapter 5. So then we finished 5 chapters already. So in total, we'll cover about like 10 chapters. Okay, so let's see. So in chapter 5, so mainly we care about this DMS, discrete memoryless source, right? And here's the diagram of the source, right? So I have a source information, and we have the coded information, right? So M is a code word that we have, right? And then we have a decoder to recover our source information, right? Okay, great. So this is basically the diagram, okay? And here's the definition for lossless block source coding, okay? And just try to remember all of them, right? So we need to define encoding function, decoding function, error, probability of error, and the rate, and then so what is the achievability, right? So what is said to be achievable, right? So we need to make sure that, okay, there exists a sequence of this kind of code, right? Not only one code, two code, right? A sequence of that kind of code, right? And so this is a function of n, right? For each different length, so we have a different kind of code, okay? And then we need to show that when n goes to infinity, the error goes to 0, right? That's how we do it, right? And then we say the infimum of all the achievable R will give you the rate of the code, okay? Very good. And then we show that, okay, so the minimum rate of the code is given by the entropy in this case, right? And remember, so it only holds for what? DMS, right? Discrete memoryless source. Okay, so it has to be IID, right? So memoryless basically means that, so it's independently distributed, right? But here we assume identically distributed as well, right? And for the proof, we have two parts: achievability and converse. Right, achievability basically means that we need to construct a coding scheme, to show that all of this condition will be met, right? And here what we use is it's called typicality coding, or we just use typical sequence, right? So basically what we do here is that, okay, so we ignore everything else that is not in the typical set, right? So we just code inside the typical set. So we give one index to each code word in the typical set, and that's it. Nothing more than that. Very simple, right? But the bad part for this is what? We ignore, everything outside of typical sequence, right? Then we have error, right? But we can show that error will go to 0 as n goes to infinity, and then we're good, right? But now you may think, okay, so it is highly theoretical, right? So in practice, we don't want this, right? Because we ignore many sequences that will happen with small probability. Right, and in practice, n is never infinity, right? It's always finite. We do not want this. Do you agree? Right, then what do we do? Will this idea still work? Any idea? Will there be an easy fix? Right, for the typical, for all the code words in the typical set, we're good, right? So it's pretty good, right? We give one of them an index. Well, this will happen with very high probability, right? But for the rest of those, for the code words that happen with very small probability, can we just code it? In other words, right? We just give them a different indices, right? For those kind of maybe longer than whatever in the typical set, right? Just give a longer code, longer indices or longer code word for each of those. Can we do that? Yeah, we can, right? So what's the maximum length we use, right? It's this number, right? So at most, hopefully I can record this. So at most, we need what? Log this number of bits, right, to encode everything actually, but we just use this to encode whatever outside. Would that be okay? Yeah, that's fine, right? It happens with very small probability. Remember, so the length we're talking about here, the R is an average number. It's average over all possibility, right? So even though each of this is very long, but if they happen with extremely small probability, we're still fine, right? So yeah, we're going to talk about that in detail later. So this is called the variable length code. So we have two different kinds of lengths. Okay, so there is an easy fix, right? So what we're covering now is not meaningless, right? So hopefully you agree with that. And then we talk about converse. Converse basically means the impossibility, right? We're going to show that, okay, this guy is actually the best we can do. Okay, R has to be bigger than or equal to this guy, something like that, right? And for the converse, we introduce you 4 important steps. Okay, so hopefully you still remember the 4 steps, right? Number 1, right? We need to write down minus whatever the conditional entropy, and right. This is number 2, right? Number 1, we have to use the cardinality bound, right? Number 2, write minus conditional entropy, and the conditional entropy will be 0, right? Then we get the mutual information, right? And then expand the mutual information in another way. So this is number 3. Number 4, final. Okay, so hopefully you remember that. For all the proofs in our class, we follow these 4 steps. Okay, so if you don't know what to do, just follow these 4 steps. Okay, then most of the point-to-point case will be following this kind of thing. Okay. Okay. Right, and then we introduce the source with memory, right? Because in practice, so our sources are not memoryless, right? Obviously, right? So basically, the symbol and symbol, there will be some dependence between those, right? For example, let's say if we have a image, right? So the JSON pixel should be dependent for sure, right? Okay, so then we need to study this kind of thing, right? How to study that? Then we introduce all the concept here, right? First of all, we model this source as a random process. Okay, so basically, we consider discrete time random process here. Okay, and then we say, okay, so the random process, we want a stationary random process, which basically means that the distribution will not change over time, right? So that kind of, but in practice, the distribution may change over time, but this is a kind of abstraction, and and it's easy to analyze, right? But it's not good enough. So basically, what we want is that we want a Markov chain. Okay, Markov chain basically means that we can ignore everything else here, right? So basically, it's just a one-step dependence here. Okay, so this is a Markov chain. Okay, and this is the easiest one to analyze, but still, it's not that easy to analyze, right? We're going to analyze that today, see how to analyze a Markov chain. Okay, and then we say information source follow a Markov chain, then it's called called a Markov source. Okay, and then we stop here, right? Any questions? All right, so let's continue for today. Yeah, today we're going to continue talking about this. So today is our lecture. Oh, 6532. Today is our lecture number 15, right? Okay, so yeah, today we'll just cover the sources with memory. All right, how spell memory? M-E-M-O-R-Y, right? Okay. Okay, so this is our chapter 4. Okay. And let's see, last class we finished talking about the Markov source, right? And then, so let's continue on that. So we're going to do a definition of a homogeneous Markov source or homogeneous Markov chain. Homogeneous Markov chain. Okay, so the homogeneous Markov chain is kind of like the stationary version of the Markov chain, right? So the transition probability does not depend on time. Okay, it's always the same. So let's see, let's say a Markov chain, MC. So that is called homogeneous, okay, or time invariant if the probability that xi equals to x given xi minus 1 equals to y, so that equals to x2 equals to x given x1 equals to y for all I. Okay, so basically it doesn't matter, the time index here, right? Just so it does not depend on time. Okay. So the meaning of it is nothing but it's one step transition PMF does not depend on time. Okay. Right, and from now on, we'll just analyze this kind of probability, this kind of Markov chain, right? So it's much easier to analyze. Okay, so because of this, then we can define the transition matrix of a Markov chain, right? So who has learned this before? Markov? Okay, you know anybody else? Okay, so yeah, it's a bit boring to you probably, but it's good. It's good opportunity to remember stuff, right? To recall stuff. Okay, so now let's define the probability transition probability matrix, right? So we say a time invariant or a homogeneous Markov chain is characterized by its transition probability matrix. Okay, so given by the following, right? For simplicity, so we just introduce you some, new notation to make our life easier. So we consider the cardinality. We let the cardinality of the total of the set is given by capital M, right? And then so we say, okay, without loss of generality. So we assume that. So this guy will just from 1 up to capital N, right? So we just have, so those are all the values, right? And those are all the states, okay, from 1 to N, right? So that we'll just use those to make our life easier. And then what we can write is as follows. So the probability, we use probability RS, PRS. So that means the probability that I equals to S given xi minus 1 equals to R. Okay, so R and I obviously in X, right? And and further we denote that, that's as this guy, right? Probability of S given R. Okay, great. And the important thing is this kind of notation, right? So this represents the transition probability, right? So here, remember, so it's a given R, and then the next step would be S, right? From R to S, right? From R to S. So that's a probability. And given this, then we can write down a matrix, right? And for this guy, we can write that as a row of a matrix, right? So basically, what we do is that we denote, so for a fixed R, we denote we say P1, right? So that basically consists of all the P1x given x in x. Okay. So we use. Okay, and so this notation means there's a row here, right? So this is a probability distribution of x. Okay, so yeah, this is the PMF of x1. Okay. So now, so this is basically a probability distribution of x1, and then we have the transition probability here, right? And let's see what we can do with both of them. So we denote this guy, so this matrix, as PRS, right? So that's the transition probability matrix. Okay, so we say that is the M times M stochastic matrix. Okay, what is stochastic matrix? So anybody heard of it? Yeah, what's that? Row. Yeah, very good. Exactly, very good. So basically, this means every row. So if both row and column submit to 1, we call double stochastic. So every row of P is a conditional PMF on our set X. Therefore, the sum of its elements is equal to 1. Right? Remember, so basically, row basically means we fix R, right? And then we change S, right? And R is the condition part, right? Therefore, the sum of the row will give you 1, right? Does that make sense? Right? So let's see an example here. So for example, we let P1 equals to 1 over 3, 2 over 3, right? And then the P can equals to the following, right? It's matrix. We can have like this. Okay. Right, so basically, so this is the distribution of x1, right? And so this basically is a probability that, 2 given x1, right? And so for this and that. Okay, so now let's compute what is the distribution of x2. Right, what's the distribution of x2? Okay, so let's compute what is P2 here, right? So that's basically the probability that x2 equals to x2. Okay, how can we compute that? Right, so basically we use the total probability formula, right? Huh? Well, I mean, this is should be a vector, right? Yeah, let's see whether it makes sense or not, right? So basically, what do we do is that, so we're going to use this, right? So we're going to use the probability of x. So yeah, this 1 basically means here, right? So this is the probability of x1, okay? So probability of x1 and the probability of x2. Oh, sorry, still x1 here. Right, and then basically we multiply this by the transition probability here, right? So this is the probability that x1 given x1, and then the probability that x2 given x1, and then the probability of x2 given x2 given x1, and then probability of x2 given x2. Right, so yeah, so we consider that's a row vector, and this is a matrix, right? And then what we have here is that, so this guy multiply this guy plus this guy multiply this guy. So what that will give you? Yeah, here there's a mistake, right? So should be x1 given x2, right? So this is basically a total probability formula, right? So this will give you, let's write it out for the first one. So that is the probability of P1x times Px1 given x2 plus the probability 1 x2 given Px1 given x2, and then whatever we have here, right? Don't write that, right? And this gives you the total probability formula, right? So the first one will give you the probability that of x2 and x1, right? And this is, well, no. Probability x1, x2, right? So this will give you the probability that x1. Oh, this is wait. This should be probability of x1, x1. This is x1, x2, right? So we have 2 here, and then So this plus that will give you the probability of P2x1, right? Total probability formula, right? And similarly, you can get that here. That clear? Everybody? Okay, great. So if that is clear, then so we can see that. So we write one more step here. So this will give you the probability that P2x1 and P2x2, right? So that's basically the distribution of x2, right? Remember, so here, so this the indices basically means x2, right? Kind of confusing here. All right, so basically that is how we compute the distribution of x2. Okay, and from here, I think it's clear on how we compute it, right? So basically, what we do here, let's recall that. So basically, what we did here is that this P2, right? So which is a PMF of x2. So that's nothing but P1. This is a kind of vector, right? We use one bar here, and times the transition probability. We use double bar here, means the transition probability. Okay, so basically we have P1 equal to this, and the P equal to this, right? So basically what we can get here is that 1/3, 2/3 multiply the matrix, right? So 2/3, 1/3, 1/3, 2/3, right? And then we can get, so it's 4/9 and 5/9, right? So that's basically the result. So this is a distribution of x2. And you can see that the distribution of x2 is different from the distribution of x1, right? Which kind of makes sense. Okay, and because of the simple relation, so we can have our propagation equation. Propagation equation, right? So that's nothing but, so the transition probability not transition probability, the probability of pi, right? So that's the distribution of xi, right? So that equals to pi minus 1 times p times the transition probability, right? Because we assume the stationary, right? Okay, and if we want to write it out, we can see that. So for each element, we use s to denote the element of the pi. Okay, so each element is nothing but this, right? So we use this minus 1 multiply PRS, and then we sum over what, R here. Okay, yeah, because R is in the, R is, remember what the indices of R is, right? R is here, right? We'll basically use this, multiply the probability of R, and then we sum over R, then get the marginal distribution for each value. Right? That makes sense? Good? Okay, very good. Okay, and so this is a propagation equation, right? Okay, and then, so what we want to say, okay, so if we keep doing this, what will happen? Right? Because, it's a recursive equation, right? We can keep going, right? So will somehow this probability will converge? Yeah, probably under some condition, right? Let's say if it's converged, so can we compute this converged distribution, or we call that the stationary distribution, because if that's not changed anymore, then we say it's stationary. Okay, so next, that if we keep doing this, so we're going to have a stationary state distribution. Okay, so how can we compute it? Right, so we say, okay, this does not change anymore, right? Therefore, we can just do what? To compute this pi here. Right, we say, if we, doing this multiple times, the pi will converge, right? Therefore, it basically means that the pi and the pi minus 1, they're the same, right? So basically, therefore, the way to compute is that we just need to compute the solution of the equation, right? Pi equals to pi times b, right? So basically it means this pi and pi minus 1, they're the same, right? Okay. Or if we can move this guy to the left, right? So basically, what we're going to get is this guy minus p, right? And this is the identity matrix, right? It's like this. So on the diagonal is all 1 and 0 in other places. Any questions? Good. So what's the meaning of it, right? So yeah, we have. Sorry, we didn't finish, right? We have this guy equals 0, right? Then we want 1 pi, right? Then does that look familiar? Yeah. What's that? Eigenvalues. Exactly. Very good, right? So that's basically the eigenvector of this matrix corresponding to 0 eigenvalue, right? But we have an important constraint here, right? The summation of all this eigenvalue has to be 1. Sorry, not eigenvalue. Summations of the elements of this left eigenvector has to be 1, right? Okay, yeah, let's write it down. So this pi here, so it's nothing but the left. What's your name? Norman. Okay, very good. Of this guy. Yeah, normally for a matrix, I need 2 bars here. I want another bar. 2 bars, right? The left eigenvalue of this matrix and the corresponding to 0 eigenvalue. Okay, and then with non-negative component, right? Because it's a probability, right? So the value in the eigenvector has to be non-negative, and sum to 1, right? Normalized to sum to 1, right? So sum to 1 is easy to guarantee, right? Just normalize it, right? But we need to make sure everything is positive. Okay, great. So yeah, this is the definition of the stationary distribution, right? The next question is that for what kind of Markov chain we can guarantee we have a stationary distribution, right? Because this equation may not have a solution, right? For what kind of Markov chain we're going to have a stationary distribution, right? So that is the next theorem. So I'm not going into detail of that, right? So I'll just go over it. Hopefully that makes sense to you. So we say if a finite state, right? So we need to consider finite state here, finite state Markov chain. So and we need 2 conditions for the Markov chain. Number 1, it is irreducible. Number 2, it's aperiodic. Okay, so now the question is that what is irreducible and what is periodic? So do you remember it? So what is it? No? Okay. Irreducible basically means the Markov chain you can get from one state to any other state. Okay, for example, let's say we have a Markov chain like this of 3 states, 1, 2, 3, right? And it's connected in this way, right? So this figure basically means that this is a state, right? And then we can go from this state to this state, okay? And then how to go from here to here is a probability, right? We have the transition probability, right? So this is a Markov chain, and you can see that we can go from one state to another state, right? So this is irreducible. And then what is periodic? Aperiodic. So aperiodic basically means that it has to be like this, right? Period basically means that how many steps it takes to go back to myself. Okay, and if the period is 1 like this, I can go directly to myself. Then it means the period is 1. If period is 1, we call that aperiodic. Make sense? Okay, so we'll consider this kind of Markov chain, right? Irreducible periodic basically means that from anywhere we can go from anywhere to anywhere with non-zero probability, right? And then I can go back to myself. Okay, yeah. Normally this concept, it takes at least like 1 or 2 lectures in random process. So
irreducible means it can go from any state to any
Yes.
other state.
Yes.
In this diagram, isn't it only possible to go from state 1 to state 3 and then state 3 to state 2? So from state 3, you couldn't go to state 1?
We can. I can go to state 2 and state 1, then go back.
Okay. So you
Yeah.
can take multiple.
Yeah, exactly.
Okay.
Yeah, otherwise it's not interesting, right? If just then it has to be every two set has to be connected, right? No, we don't need that.
Okay.
Yeah, I mean, yeah, what I said is like, I think what I said is kind of like, that implies irreducibility, right? I think the definition is that, from one state, there's a non-zero probability that you can go to another state or whatever, right? Yeah, and for aperiodic, so I think the official definition is that, okay, then let's say, I don't want to go that far, but something like this, right? Let's say we don't have that, and then I can, in order to go back one, I can go from 3 to 1, right? That's one way, right? Let's say if I have, let's say if I have another line here, right? I can go back to 1 from 2 to 1, right? Then the period is 3 and 2, right? So basically, and then you need to compute some greatest common divisor or whatever, right? So yeah, probably in that case it's also aperiodic, but you consider it's the simple case. I think the greatest common divisor, as long as the greatest common divisor for all periods, for all periods is 1, then it's aperiodic, something like that, right? So yeah, I think this is an example. It doesn't have to be like that exactly, I guess, right? But yeah, this basically means nice Markov chain. Okay, and then we say then the stationary distribution. In this case, we can guarantee that we have a stationary distribution, and we can guarantee even it is unique. Yeah, but if you are interested, just read more about Markov chain, right? Yeah, for the discrete Markov chain, in my grad school at USC, so I took a class only on this Markov chain, right? There are a lot of things to explore, right? It's not that simple, but we just need those more or less. Okay, and the stationary distribution is unique, and then for any initial state PMF, okay, P1. So we have the following formula. So basically, the limit n goes to infinity, then Pnx equals to pi x. Okay, so this is nothing but PMF of xn. Okay. So it basically means that if a Markov chain is irreducible and aperiodic, then we just proceeding whatever we discussed before, just compute this, and then it will converge. Okay. So what is converged distribution? It just solve this. If you solve this, then you can get the converged distribution. Okay. So next, let's see some implications of this theorem. So one immediate implication is that, okay, so what if we just start with the stationary distribution, right? And then the Markov chain will not change anymore, right? So if this Markov chain is not changing anymore, then so the random process formed by this Markov chain would be a stationary process, exactly, right? So we say if a finite state irreducible and aperiodic, okay, again irreducible, aperiodic Markov chain, so that is initialized with its stationary distribution. So this basically means that P1 equals to pi, okay? Right, or P1x equals to pi x for all x here, okay? Then the Markov chain forms a stationary process or stationary random process or the homogeneous Markov source is stationary. Okay, so this is obvious, right? So if we start with pi, and then of course, and nothing will be changed, right? So it will be a stationary process. Okay, so that's how one way to build the stationary process. Okay, so that's what we're going to study. Right, and the second topic in this class is that, okay, so now let's consider this kind of source, right? So now we have a source with memory, right? The source is a stationary random process, okay? So it doesn't have to be a Markov process yet, but we have a random stationary random process, okay? So now we want to define, what we want to encode this random process, okay? How can we do that? So we need to introduce a concept of entropy rate, okay? So let's see why we need that, right? So okay, so now let's consider. So yeah, based on what we have learned so far, so can you give me a coding strategy for a random process? Let's say it's a finite length, okay, n, from x1 to xn, right? If I give you this, so can you give me a coding strategy? Right, based on what we have learned so far. Right, how about we consider that the whole thing as one symbol? Right, consider this from x1 to xn as one random variable. It's a random vector, right? So what if we consider that as a whole one random variable? So do you know how to code it? Really? Yeah, we know how to code one random variable, right? Of course, we can consider there are like multiples of those. Go on forever, let's say. In that case, you know, right? So just use what we learned before, right? Okay, so basically, yeah. So what we're going to do is that, right? So let's assume a discrete. For discrete information sources, right? And we have vector from x1 to xn, right? So in that case, we know this is this number of bits. So it's what we needed to encode the random vector. That makes sense, right? Before, we consider if n is 1, and then we need h of x, right? But now let's consider that as a whole, right? So yeah, we may consider that like multiples of those, right? And then we just use whatever we learned before, the entropy, this AEP coding, right? Typical coding, right? And then we can show this is the number of bits we need. Okay, sort of like that. Or at least intuitively, that should be the number, right? So hxn bits of information is needed for the decoder to recover xn. Okay, and now let's go back to the case that we learned before, right? So we consider a DMS, discrete memoryless source, right? And then we need what? At least r equals to, so if we normalize it by n, right? If we consider xn, they are memoryless, right? So, and then this equals to 1 over n times hx equals to hx bits, right? Bits of information. Right, so this is what we need, and this is what we learned before. Okay, so now let's consider the source with memory, right? So if we consider the source with memory, so we need, if we normalize it by n again, we need this number of bits of information. Okay, Yeah, so this is the this number of bit information per symbol to recover xn, right? Okay, very good. Okay, and so basically, yeah, this is the idea, right? So now the question is, does that make sense or not? Okay, so this is a kind of intuition, right? So we're going to prove that, or, yeah, for this kind of thing, so is there a way to compute it? Right? So we do not want to compute this, right? So it's the entropy of a whole vector, okay? Right? Is there a way to compute that in an easier way, right? So that's basically our idea. Okay, so so this kind of thing is like, if we compute the entropy of a random vector, right? And then we normalize it by n, right? And if we let n go to infinity, so this is kind of like what? Like a rate, right? So this quantity is basically called entropy rate if we let n go to infinity. Does that make sense? Okay, so let's write it down. So the entropy rate of a random process, let's say xi, I from 1, 2, 3, and so on, over x. So this is defined by, so we use this notation, it's calligraphic x. Yeah, this is defined, so this is the definition of the entropy rate, right? But so it only makes sense when this limit exists, right? If this limit does not exist, then we don't have a definition of the entropy rate. Okay, so when limit right, otherwise it is undefined. Okay, so now let's consider some special cases, right? Again, so for a DMS, okay. So remember that when we talk about DMS, discrete memory source, we talk about the IID source, right? So we have an independently identically distributed process, okay, and with marginal px, okay, that's the same for all the x. In this case, our entropy rate is nothing but hx, right? Because there are ID, right? If we can take this n out, and then that'll be equal to hx, right? So it's very good. And now let's go one step further, right? Let's say for a sequence of independent but not identically distributed random variables, okay, sequence of this kind of random variables, and then so we have for each random variable we have this distribution, okay, and then we have, okay, in that case you can see that so for each xi h is different, right? So in this case, so our entropy rate will be given by this, right? Yes, well, there's a sum here. Right, if the limit exists, okay? And you can see that basically this means that if they're independent, right? So by the property of mutual of entropy, then we can break them, right? So we have a summation here, okay? Right, and right, that's basically its entropy rate. So any questions? Yes.
So why isn't it like calligraphic X this time? The left-hand side.
Y, it's not, it's capital X. Yeah, calligraphic is this one. You mean this X?
No, like the left one. So it is
Yeah.
calligraphic X?
Yeah, so this is entropy rate.
Oh.
Yeah, so yeah, this is calligraphic, this is calligraphic. So I just want to give you two examples how to compute the entropy rate. Okay, so yeah, one case is when there's a DMS source and the other one is independent but not identically distributed source. Okay, for both of them, they are easy because, so we can break this, right? So we can take this n out somehow, right? Because they're independent, right? So, okay, yeah, so that's basically it, right? But now let's go to the case where it's the most complicated case, right? So they're not identically distributed and they're not independent. Then what do we do, right? So we do not want to compute this, right? Because computing that is very, very difficult, right? Why is difficult? Because there are like so many number of terms there, right? So it's combinatorically large number of terms here, right? If you compute that, it will be horrible, right? So there's an easy way to compute that, turns out. So we have a theorem here, right? So for a stationary process, xi, it doesn't have to be Markov, right? You just want stationary here. Over x, we have, so hx, so the entropy rate, that's given by this. Right, let's see that whether that makes sense or not, right? So the only thing we need to compute is a conditional entropy. Okay, and xn given by all the past information. Okay, and then when that n goes to infinity, and then we're good. Okay, is that clear? Right, this is a theorem, right? So then we need to prove it. Okay, so yeah, let's see. Yeah, let's use 2 minutes to prove the first step, right? And then we're going to continue next lecture, right? So yeah, proving that is not very easy, right? We're going to use a very powerful tool from analysis. Okay, so basically what we're going to do is that first step is that we're going to show this function is a non-increasing function with n. Okay, so basically means that if it's lower bounded and somehow decreasing or non-increasing, then we can at least say the limit exists. We don't know what the limit is, but the limit will exist, right? That's how we show it. Yeah. The first step is to show that the limit of this guy exists, right? So yeah, but we don't know whether it will convert to entropy rate or not, but first step is to show it exists. And then we're going to show, okay, actually the converged value would be equal to the entropy rate. That's the idea, okay? And prove that, that exists is very easy, right? So basically this is what, so we just do some manipulation here. So we move one step further, okay? We consider n plus 1, right? And then, so this will just equal to this, given xn minus 1, and so on till x1, right? And then, so we can show that, so if we reduce, drop this x1, right? So we just drop it. And then, so we're going to have an inequality, right? We have an upper bound of it, right? Because condition is always reduces entropy, right? So we have less condition, then the entropy will increase, okay? Right, and then because we have a stationary process, right, then this will equals to xn given xn minus 1 up to this, okay? So this step we use conditioning reduces entropy, okay? And this step we used is a stationary random process. Okay, right, and from here we could conclude that this guy is a monotone, non-increasing sequence with respect to n. Okay, and then we need one more condition, right? Is non-increasing, but it's lower bounded, right? Then what is the lower bound? Right, it's almost decreasing, and then if we have a lower bound for it, then we can say it will converge, right? And what is the lower bound? It's entropy, right? So can you tell me a naive lower bound?
0.
Exactly. Lower bound at 0, right? And then we say the limit exists, right? It has a limit. Okay, and this is the first step, okay? And then from next class, we're going to introduce the second step. So then we're going to show this limit is actually the entropy rate. Okay, and okay, so let's end for today. Okay, thank you.